Do you split your world into bananas and non-bananas? No? Then why do you split your systems into linear and nonlinear? Hello, my name is Gregor Böhm and my research is focused around harmonic distortion, a well-known nonlinear effect in RF engineering. So what is harmonic distortion? If you have an RF signal with a fundamental frequency of omega and you transform it in a nonlinear way, your signal will get distorted and you will gain additional frequency components. Mathematically, you can represent it as a sum where the first term of the sum is your fundamental at the fundamental frequency omega. The next term is the second harmonic with twice the frequency of the fundamental and so on. Basically, every time your signal interacts with a nonlinear element, you will get harmonic distortion. How can these harmonics cause system problems? I have two examples. I have a system with a signal generator Tx and an antenna and a DBS diode in between, which is an EST protection device. When we send an RF signal from Tx to our antenna, the signal interacts with the DBS diode and generates harmonics. These harmonics are then radiated by the antenna. The nonlinearity does not have to be in the signal path. It can also be coupled into the signal path. Why does a diode cause harmonic distortion when the signal only passes by? The answer here is the nonlinear voltage-dependent capacitance of the diode. Over one period of our RF signal, the capacitance is changing. Thus, we have an interaction between the signal and a nonlinear device. Nonlinear capacitance is not the only source of harmonic distortion. As we can see here, we have two interfaces in contact. These interfaces are not perfectly smooth. As a result, the contacts can be modeled as a nonlinear resistance in parallel with a nonlinear capacitance. When an RF signal passes through such an interface, these nonlinearities lead to the generation of harmonic distortion.
Then there is coming up the question how to effectively measure the harmonic in an RF system. And one of the biggest challenge for measuring the harmonic is we want to get a really clean source. The standard signal generator, by generating the fundamental signal, they also have the harmonic generated out from the signal generator. Typically, it's 50 dB below the fundamental. In most of the case, it's no problem. We won't get bothered by this harmonic. But for measuring the harmonic in the RF system, it's not sufficient enough. For example, if you want to measure the contact harmonic, in some case, that the harmonic compared to the fundamental signal will be 100 dBc below the fundamental. And at that moment, if you have too strong system harmonic, they will be dominate your harmonic measurement and you will not be able to see the DUT's performance. To overcome this, there are two main goals of the harmonic test that need to be achieved. It needs to be filtering and also amplifying the fundamental signal to have a strong enough, also clean enough fundamental signal. And then the system also needs to separate the harmonic signal out from the fundamental and prevent to disturbing the measurement. Let's break down the basic system structure. We will need to have the signal generator at least to generate the fundamental signal. Then, to drive the DUT hard enough to produce measurable harmonics, we need a powerful fundamental signal. Typically, it is more than 20 dBm. Since standard signal source lacks sufficient output, a power amplifier is required. Because the power amplifier is also a nonlinear device, it generates its own significant harmonics. We insert a low-pass filter immediately after the amplifier to reduce the harmonics coming from the source and the amplifier. Then it's coming to the core part of the measurement, the duplexer. This is the heart of the setup. The fundamental signal enters the low band port of the duplexer for further reduce the harmonic before reaching the DUT via the common port. Harmonic generated by the nonlinear source in the DUT will propagate in both directions. The forward harmonic are terminated at the other end of the DUT. the reverse harmonics will travel back to a duplexer and distribute to high band port, then measured by the spectralizer. The high band port guides only the harmonic signal into the spectralizer while blocking the high power fundamental signal if the fundamental signal is too strong to feed into the spectralizer. This signal could generate internal harmonic inside the spectralizer and then dominate your harmonic measurement. You will no longer able to see the harmonic coming from the DUT. In this video, we want to present two types of the harmonic test setup to you. One is the TVS style harmonic test setup. Another one is the contact harmonic test setup. They share the common concept we introduced in previous section, but based on their application, they have divided into the different function and the component selection. So on my left side, this is the TVS style harmonic measurement setup. This used to characterize the harmonic performance of the TVS style. On the right side, there is the contact harmonic measurement setup. This one is used to characterize the contact induced harmonic under the different pressure and the conditions. Here, we will give you the demonstration about how to measure the harmonic induced by the TVS style. That first of all, you will need to have the signal generator. We will generate 860 megahertz of the signal. We use the RF module from another system as an amplifier to boost up the signal to 20 dBm. Then the signal will feed into this RF module box. This contains all the filter and duplexer we introduced in the previous section to get the clean signal to our DUT, in this case, the TVS style. And then when the TVS style generates a harmonic, the reverse harmonic will be measured by the spectralizer. Here you can see at 2.58 gig, which is the third harmonic of our fundamental signal. As you can see, the third harmonic is minus 55 dBm. By comparing the fundamental input power, which is 20 dBm, there is 75 dBm of difference. Without all the filtering procedure we have done in the RF module, we will have a difficult time to see such a signal. So for testing the contact harmonic, we constantly having the problem, have the poor repeatability, and also the testing accuracy is suffering from the instability of the testing setup. So here is our contact harmonic setup. For this setup, we want to provide the high output power, and it also have a really stable mechanics. And then it could do the fully automated test, and we can test our sample over and over again to get the static result out from it. First of all, we still need the signal generator to give us the fundamental signal. Then we build our RF module, which include all the amplification and filtering stuff inside. And once the signal feed in, it's first go into our power amplifier over here. This power amp could provide around 45 dB of the gain. After boosting up the signal, the power amp feed into the 3 dB attenuator. This attenuator is a protection device to prevent the open circuit that have a strong reflection back to the amplifier and damage it. After that, we have the tubular filter. This is the low-pass filter made by ourselves. This filter could handle more than 100 watt of power. After the 3 dB attenuator, it's the low-pass tubular filter. This due to the structure of the filter, this could handle more than 100 watt of power. This filter could provide more than 50 dB of the rejection to reduce the self-harmonic coming from the source. And then it's going into the direction coupler. This direction coupler helping us to monitor the forward power with another log detector. Then the forward fundamental signal will go into the duplexer. This duplexer will even further reduce the self-harmonic. And from the common port, it's sending out the clean signal to our test fixture. So here, then we come into our test fixture. Due to the contact harmonic, it has really low repeatability, and the stability of the system is a critical part. In this case, we have this robot arm control system that could helping us to do the testing over and over again with a really consistent and stable press. We have the force gauge mounted over top, And then we have the adapter fixture for mounting the DOT. For example, when we want to test the copper tape, we'll put a piece of copper tape over the top. Once the signal sending out into this PCB, and the robot arm will get controlled by the computer to keep pressing down. During we pressing, we will keep recording the harmonic reading and the force gauge reading and record this simultaneously. And of the forward direction, we will terminate our signal, and we will only measure the reflect harmonic in this case. The reflected harmonic will coming back to this port, and then separate by the duplexer to the high band port. We add additional high-pass filter over here to even further reduce the fundamental signal because the power we're sending forward is too strong. And after that, it will go into a spectralizer to measure the reflected harmonic.
The question I asked at the beginning of this video originates from a famous quote. Splitting up your world into linear and non-linear systems is as reasonable as splitting it into bananas and non-bananas. This quote is meant to emphasize one thing. There are far more non-linear systems than linear ones. Even if you design a system to be linear, it is very likely that some nonlinearity is still present. Either because you add EST protection in the form of a DVS diode or because of a non-linear contact that you may not even be aware of. In all cases, we now know that every time a signal interacts with a non-linear element, harmonics are generated. And now you know what harmonic distortion is, how to look out for it, and how to measure it.
You're the signal in my static